Welcome everyone to our explainer on threat modeling. Now, if you're building any kind of software, or especially if you're getting ready for a security exam, this is a topic you absolutely have to know inside and out. We're going to break down the first part of this whole process, step by step.
So, here's our game plan. First, we'll cover the absolute basics, the fundamental concepts. Then, we'll zoom out and get a bird's eye view of the entire process. After that, we're going to roll up our sleeves and learn how to actually decompose an application and then hunt for threats using a really powerful framework called Stride. And finally, we'll wrap it all up with the key takeaways you need to remember.
All right, let's dive right in with Section 1, the basics. Before we can even start to model threats, we have to be speaking the same language. Getting these core ideas right is absolutely essential, so let's start there.
So what is the whole point of threat modeling anyway? Well, it all boils down to one simple goal: to identify the most important parts of your application, your assets and functionalities, and then figure out how to protect them. You can think of it as being proactive. Instead of just waiting around for something bad to happen, we put on our attacker hat from day one. We ask ourselves, what are our crown jewels here? Is it the user data? Is it the payment system? Once we know what's truly valuable, we can focus all our energy on defending the things that matter most.
Now, the word threat gets thrown around pretty casually in everyday life, kind of like in this cartoon. But in our world, in the world of cybersecurity, words like threat, vulnerability, and risk have very, very precise meanings. So let's define them properly, because I guarantee you'll see these on your exam.
First up, let's talk about vulnerability. Now, for your exam, you'll want to know this exact definition. It is, vulnerability is nothing but weakness in the system which will aid the attacker in successful execution/exploitation of the threat. Okay, so what does that actually mean in plain English? Just think of it as an unlocked door. It's a weakness. For example, let's say the threat is that your server gets knocked offline. Well, having a very low bandwidth connection would be the vulnerability. It's that specific weakness that an attacker can exploit to successfully launch their attack.
Okay, so if a threat is what could happen, and a vulnerability is the weakness that allows it to happen, then what is risk? Well, risk is what you get when a threat meets a vulnerability. The formal definition, which you should know, is the potential loss/damage of an asset as a result of a threat exploitation using vulnerability. Basically, it's how we measure the actual danger. See, you can have a threat with no weakness, or a weakness with no threat, and in both those cases, your risk is pretty low. But when those two line up perfectly, that's when you have a high risk of something really bad happening.
So let's quickly recap some key aspects here. Threat modeling is a high-level security analysis. It's about finding all the doors and windows into our system. It is definitely not a code review. We're looking at the bigger picture. And here is the most important takeaway from this slide, something you absolutely need to know for your exam. Threat modeling is done during the design phase of the software development lifecycle, or SDLC. Why is that so important? Well, because fixing a security flaw on a blueprint is 1,000 times cheaper and easier than trying to fix it after the skyscraper's already built.
Great, now that we've got the vocabulary down, let's zoom out a bit and look at the overall process. This will give you a kind of roadmap of how a threat modeling exercise actually works from start to finish.
The whole journey usually starts with what's called a kickoff meeting. This is where you gather all the project's blueprints, the technical documents, and you figure out what those crown jewels are that we need to protect. Then you start drawing. You create a simple, high-level map of the system, which we call a level 0 diagram, to an initial analysis, and then review it with the system architect to make sure you're on the right track.
After that first sketch, you zoom in with a more detailed level 1 diagram, adding more specific components. Then, you just rinse and repeat that analysis and review cycle, going deeper and deeper if you need to. After that comes the ASF, or Application Security Framework step, where you create a practical checklist for the developers. And finally, everything gets bundled into a final report that you present to the team, giving them all the information they need to build the right defenses.
You can really boil this entire, complex-sounding process down to just 3 core stages. 1. Understand the system. 2. Find what could go wrong with it. And 3. Figure out how to stop it. That's it. So let's dive into Stage 1.
Stage 1 is all about decomposing the application. I mean, you can't really defend a castle if you don't even know its layout, right? So our main tool for this job is the Data Flow Diagram, or DFD. This is how we create that visual map of our system.
Okay, this is really important. You'll probably need to know this for your exam. Every data flow diagram is built from 5 essential elements. The circles represent processes. That's your code, the stuff you control. The squares are external interactors. That's other people's stuff, like users or third-party APIs. The 2 parallel lines represent data storage, like a database.
The arrows, of course, show the data flows. And finally, that dashed line represents a privilege boundary. And this is a critical concept. It shows where trust levels change, like going from a user's web browser into your secure server.
Okay, so once we have our map, our DFD, we move to stage 2, finding the threats. And for this, we use a really powerful framework that came from Microsoft, called STRIDE. STRIDE is an acronym, and it basically gives us a systematic checklist for brainstorming all the different kinds of threats. Let's go through it, letter by letter.
The S in SPRID stands for spoofing. This is all about identity. Think of it like identity theft, but for systems. The key questions you ask here are, how do we know someone is who they claim to be? And on the flip side, how do they know we are who we claim to be? Spoofing is simply the threat of impersonation.
Let's apply this to our diagram to make it real. An attacker could try to impersonate the Geneva service. If they pull it off, they could start sending malicious data to our cache server. So the core question here is, how does our server know it's talking to the real Geneva and not an imposter? This is a classic spoofing risk. So how do we stop an imposter? The exam critical answer here is authentication. And for server-to-server communication like this, the gold standard is something called mutual authentication. Think of it like a secret handshake where both sides have to prove who they are. Our server shows its ID, and Geneva has to show its ID right back. They both verify each other before any real data is exchanged. Things like certificate pinning add even another layer on top of that. Next up, let's move to T for tampering. This threat is all about the unauthorized modification of data. We have to ask, can someone change our data while it's flying across the network, or maybe while it's just sitting in our database? This is fundamentally an attack on data integrity.
Looking at our diagram again, we see the cache server sends logs to Geneva. That data flow right there is a potential point of vulnerability. An attacker could intercept those logs in transit and change them, maybe to hide the evidence of their own attack. So the question becomes, how do we make sure the logs that arrive at Geneva are the exact same logs that were sent?
To protect data that's on the move, data in transit, we use protocols that guarantee integrity. The most famous one, of course, is HTTPS, which uses something called Transport Layer Security, or TLS, to create a secure channel. For data that's just sitting there, data at rest, we use things like digital signatures. These countermeasures are like creating a digital seal on the data that breaks if anyone tampers with it, letting us know something is wrong.
The R in STRID is for repudiation. You can think of this as the I never did it threat. It's when a user can perform some action and then later plausibly deny that they ever did it because you don't have any proof. This is really an attack on accountability. Can a user get away with saying, "It wasn't me"?
In this scenario, let's imagine a build client requests a package from our server. Later on, that client could claim, hey, you never sent it, or maybe you sent the wrong thing. If we don't have solid proof, how can the server defend itself? It needs what we call non-repudiable evidence.
So how do we build that proof? The answer is logging, and lots of it. Robust application logging, detailed audit logs, and secure event logs all work together to create an undeniable paper trail. By recording who did what and when they did it, we make it pretty much impossible for users to credibly deny their actions.
I stands for information disclosure. This is a classic threat to confidentiality. In other words, a data breach. The questions here are simple. Can someone who isn't authorized read our data while it's in transit? Or can they access it while it's just stored on a disk? It's all about keeping secret secret. Let's go back to our example of logs being sent to Geneva. If that data flow isn't protected, an eavesdropper sitting on the network could just read everything as it goes by. This is a classic man-in-the-middle attack, and it's a direct violation of our data's confidentiality. The number one defense against information disclosure is encryption. We use encryption in transit, once again, that's where things like HTTPS and TLS come in, to protect data on the move. And we use encryption at rest to protect data that's just sitting in a database or on a hard drive. And here's a key tip for your exam. Make sure your application's error messages don't leak secrets. An error that says login failed for user admin just told an attacker that admin is a valid username. That's a form of information disclosure. Next up is D for denial of service, or DOS. Now, unlike most other attacks that are trying to steal or change data, the only purpose of a DOS attack is to shut you down. The entire goal is to make your service unavailable for your legitimate users.
So a malicious client could attack our cache server in a couple of different ways. First, they could just flood it with so many requests that it gets overwhelmed and can't respond to anyone else. Or they could be a bit cleverer and keep requesting huge, unique files over and over again to completely fill up the server's disk space, crippling its ability to cache things for other legitimate users.
And finally, we have E for elevation of privilege. This is one of the most dangerous threats out there. It's where an attacker finds some kind of flaw that acts like a ladder, allowing them to climb from being a low-privilege, regular user all the way up to being a super powerful administrator.
So how could this work? An attacker on the build client could send a specially crafted malicious request to our server. If our cache server has a bug in the way it handles that request, it could be tricked into running commands for the attacker. And just like that, the attacker isn't just a client anymore. They effectively own the server.
Mitigating this is absolutely crucial, and you'll want to remember these for your exam. First is the principle of least privilege. This means you always run your services with the absolute minimum permissions they need to do their job, and nothing more. Second, you enforce strong access controls. And third, you live by the golden rule of security. Treat all input from users as hostile until you've proven it safe. You have to validate everything.
And that is a full tour of the Stride framework. We've covered a lot, so let's wrap this up by quickly hitting the most important takeaways from this whole explainer. This slide really highlights the two different hats you wear when you're threat modeling. First, you're an architect, working in design view, drawing the map of the system. Then, you put on your detective hat and switch to analysis view, where you systematically use frameworks like Stride to hunt for weaknesses in that map. The specific tool name isn't important for the exam. What's crucial is that you understand this two-step process of drawing and then analyzing.
So now that you understand the basics of threat modeling and you've seen the Stride framework in action, you're going to start seeing the digital world a little differently. So I'll leave you with a question to think about. What's the first vulnerability you'd go looking for in your favorite app? Thinking like this is the first step to becoming a security professional. Thanks for watching, and good luck on your exams.